Welcome back. We were discussing about the applications of Laplace transform, and we have solved first order and second order linear ordinary differential equations, and also a system of linear ordinary differential equations. We have solved how to solve. We have seen how to solve these problems. So let's. We have also solved some special equation. It's called Bessel equation with boundary conditions, rather initial conditions. You have seen how to get that solution by making use of initial value theorem. We will also look at a similar problem. So let's do one more problem in this video, and along with we will solve. We will also solve partial differential equations, along with some more equations. Okay. In this video, to start with solve some second order ordinary differential equation of similar type, like what I have done in the last video. It's like a kind of equation, second order equation with variable coefficients, and then with some initial conditions. How do we solve it? So here also we may have to use the initial value theorem, and then we'll move on to solve other applications. For example, solving partial differential equations. We start with the first order. We'll try to solve one or two problems, and then we move on to typical linear equations, which is hyperbolic, wave equation, heat equation, and Laplace equation. We try to solve, and then as an applications. Okay, and then we'll solve. We'll give applications how to solve as an application of this Laplace transform. We can also solve integral equations. This is what we will see, some special type of integral equation, which you will see in the next one or two videos. Okay, so let us start doing this one more example. So that is solve d square x by dt square plus t dx by dt minus 2x equal to 2. So this is what you have to solve, and t is positive, domain is 0 to infinity, and you have these initial conditions. This is 0, and also x dx by dt at 0, this is also 0. Okay, so these are the two initial conditions. So you can look at the solution. Solution is apply Laplace transform, same Laplace transform to get to the equation. We get Laplace transform of two derivatives, that is s square x bar of s minus s times x at 0 minus x dash at 0. So these two are the conditions which I am using here, so that makes it 0. So this is what you have for first term. Second term, you have the minus dds of Laplace transform s times a Laplace transform of dx by dt. Sorry, minus dds of Laplace transform of this one when t is multiplied with this. If you want to have a whole transform of t times this one, what it is minus dds. You have seen when we are doing properties of the Laplace transform, you have seen the derivative of Laplace transform of this is minus dds of Laplace transform of coefficient of t, that is Laplace transform of dx by dt. That we know already that this is x bar of s minus x of 0, that is anyway 0. So you have this one, and then minus 2 x bar of s equal to 2 times, and you have the Laplace transform of 1. So that is 1 by s. So you have 2 by s. We really do not know what is the domain of this s. Okay, so s is because that really we do not know, because that is an unknown function, and only because we know only the domain t positive, we are just applying it here along with these initial conditions we have used, and this is what we have. So you have x bar of s. If what you get is okay, let me use this s square, and then minus x bar of s, and then minus s times d ds of x bar of s minus 2 x bar of s equal to 2 by s. So this becomes s square minus 3 times x bar of s minus s times dx bar of s by ds. This is equal to 2 by s. So, this you can rewrite as dx bar of by ds minus s minus 3 by s of x bar of s. I divide with s both sides. So, that you have this is going to be minus 2 by s square. So, now we need to solve for x bar of s. So, this is a linear equation, linear ordinary differential equation with s variable. So, one can solve by multiplying an integrating factor as e power integral this is as your p that is minus s minus 3 by s ds. So, this is our integrating factor. So, you get e power minus s square by 2 times plus 3 ln of s. Simply you get it as s cube times e power minus s square by 2. So, if you multiply this both sides of this equation, you get s cube e power minus s square by 2 times x bar of s, whose derivative is nothing but after multiplying this left hand side. That is your left hand side, and you already multiplied this side with s square times s cube e power minus s square by 2, which is minus 2s e power minus s square by 2. So, you can integrate and get this x bar of s times s cube times e power minus s square by 2 is actually equal to minus integral 2s e power minus s square by 2 ds plus an arbitrary constant c, integration constant. So, this one you can easily see that this is going to be e power minus s square by 2. So, times 2 comes out, and this is exactly what you have. So, this is your antiderivative for this integral. So, you have integral value is this plus c. So, if you now from this you can get your x bar of s as 2 by s cube and then plus c by s cube times e power s square by 2. This is what you get as a solution x bar of s. Now, you can invert this. See, as you can see, you have already used your initial conditions, both the initial conditions we have used here. So, there is nothing to use, but still we have an arbitrary constant, c is an arbitrary constant. So, this we may have to use, we have to find out. So, as you can see, this is you have only 0 is the singular point in your s plane. So, 0 is the same. So, you can use your c minus I infinity, c infinity, c plus I infinity, that inversion any curve c with c positive. Okay. So, otherwise e power s square by 2 is an analytic function, only s cube having a singular point at 0. So, all the this side. So, this side you can see that this function is analytic function. So, that is how you choose your this line c value, so that you can get your x of t from your inverse definition of inverse Laplace transform. So, or otherwise you can get x of t directly. So, 2 by x cube is 2 by s cube is actually is your t square. So, Laplace inversion of this is your t square plus c times Laplace inversion of e power s square by 2 by s cube. Okay. So, this is a function of t, right. So, you know that if you want to use your initial value theorem x of 0, that is 0. So, you can see that this is 0 is x of 0, this is a limit of x of t as t goes to 0. So, x of t is satisfying the differential equation. So, it is differentiable. So, its limit exists. So, this is the one which is equal to a limit of s times x bar of s as s goes to infinity. So, what is this one? This is equal to limit s goes to infinity s times x bar of s is 2 by s cube plus c divided by s cube e power s square by 2. So, this if you want this if you see, this is going to be, if you remove you have s square, here also s square. So, this is going to be anyway, first term is going to be 0 plus second term, this is going to be the limit s goes to infinity by s square e power s square by 2. Exponential function grows bigger than s square. So, this limit is infinity, but this left hand side, this is 0. So, for this implies c has to be 0. So, this gives me, because of this, once we find c is 0, so this implies the solution x of t is simply t square. So, this is your solution of this initial second order differential equation with the initial data. So, x is non-homogeneous equation, in fact t square, if you substitute, you can verify t square if you differentiate initial conditions satisfied, t square if you do it here 2t, and so here 2, and if you put it here t times, so 2 plus t times 2t minus 2 times t square. So, this goes to 0 and this is left with 2. So, that is exactly satisfying. So, equation is satisfied along with this initial condition. So, the solution is, required solution is only a t square. So, this is how you solve second order equations, even if it is non-homogeneous equation. You don't have to worry about non-homogeneous terms separately. You can just use Laplace transform, directly get its inverse, and you can get this. You can use that way. So, some places you may have to use your if you get an arbitrary constant, you can use your initial value theorem or final value theorem depending on what is given. If it is given as x at 0, that is initial value theorem you can use. If you have x at infinity, if you have a boundary condition. So, for example, what is the boundary here? So, this is t equal to 0 and this is at infinity. So, at infinity, if you provide two boundary conditions, let us say x infinity, x of t goes to 0 as t goes to infinity, let us say. If you want to use this one, you can use a final value theorem, okay, if you to get rid of the arbitrary constants involved in your Laplace transform at the end. Okay. So, instead of this, if you are given this, still you can solve as though this is an unknown. So, when you are applying Laplace transform for the second derivative, you will get dx by dt at 0, that you take it as some constant a. So, a will be there throughout, that a you can get it by applying this boundary condition to get rid of this a. And if it still, if you can in the inversion, when you solve this equation, if you still get some another arbitrary constant, that you can use it either with this initial value theorem because of this condition, or with this final value theorem you can use to get rid of that arbitrary constant involved in the solution of the ordinary differential for the first order differential equation of for x bar. Okay. So, you can use the, if you want to use this one, you have to use final value theorem. If you want to use this initial condition, first one, this boundary condition, if you want to use, you can use the initial value theorem. If you want to use this boundary condition to get rid of that arbitrary constant that is coming at the end, for example, this here, this you can use this arbitrary constant, this boundary. This boundary condition, if you want to use, you have to use final value theorem. Okay. So, that is how you make use of those two simple results that I have explained few videos, last few videos. Initial and final value theorems, they are also called Tauberian theorems. So, they are useful in somewhere else, but for our purposes, these are the only, these are the place you can use these those two initial and final value theorems. Let us move on to solve not only, so as I explained, you need not be given two initial conditions, x at 0 and derivative at x equal to 0. If it is, you can also get some, if your domain is only, if your domain is this, and if you need, you can get this boundary condition. If you have a boundary condition like this, still you can get this as a solution. Okay. For example, if you still can get, if your domain is this, you are looking for x of t for all t positive, but what is given is x of 0 is 0 one condition, and suppose you want to give somewhere else some other condition, let us say some at 1. then x at 1 if it is given, say let us say 1, then still you, as though you know that x dash of 0 is some arbitrary constant which you use. So, once you use this, you will see that x of s, this differential equation will have this arbitrary constant a, that along with that, once you solve this differential equation, that a and c, you will get an arbitrary constant of integration, you get two arbitrary constants a comma c. A you can get it from this, and c you can get it by initial value theorem, or basically initial value theorem, because you know x of 0 is 0. So, like that we can do. So, let us do some example of some, such problem. Let me use some simple example. Solve y double dash, so that is dx, let me use dx, okay, dx by dt, d square x by dt square plus x of t, this is x of t, okay, this is x equal to t, and this is t positive. What is given is x dx by dt at x equal to 0, at t equal to 0, that is given as 1, and x at pi is given as 0. So, suppose you have so as I explained this, you have the t is positive 0 and you have up to infinity, you can get it up to 0 to infinity, and what is given is somewhere in between you have at pi you have the value of your unknown function. So, let us try to attempt to get this solution. So, apply Laplace transform as usual. Laplace transform gives from gives what you get, you can write this as s square x bar of s minus s times x of 0, and then you have minus x dash of 0, that is given as 1. So, let me put it here, and plus x bar of s, that is the Laplace transform of this second term, and Laplace transform of t is 1 by s square. So, I used this condition so far, I have not used this one. So, this is still unknown x of 0. So, let us say this, you call it, let x of 0 is unknown, that is a, okay. So, you have s square. So, you have 1 plus s square times x bar of s, and then you have minus is equal to 1 by s square plus 1 plus s times a, x of a is a. So, this is actually equal to s square 1 plus s square plus s cube a, and you can get this x bar of s as 1 plus s square plus s cube a by s square times 1 plus s square. So, this is you can get it as 1 by s square first term, and second term you can get it as s a by 1 plus s square. Okay. So, you can easily get your inverse Laplace transform gives now x of t, and the 1 by s square is simply t, and this one will be a times, and you have s by 1 plus s square plus 1, that is cos or sin, cos, right. So, cos t. So, cos t is s divided by s square plus 1, the Laplace inversion of this is cos t. So, I have used this. So, this is the solution I have derived. So far I used only this one, but I did not use this one. So, I use this one to get rid of this a, and also you can also use okay. So, initial value we cannot use, initial value theorem we cannot use, because x of 0 is not known, still it is an unknown. Okay. So, let me use so if I use, let me see what is the initial value if I use x of 0, which is a, which is equal to limit s goes to infinity s times x bar of s. What is x bar of s? That is simply 1 by s square plus s a by 1 plus s square. So, if you calculate this, that is going to be 0, and here s square by this, that is simply a. So, a equal to a, you do not gain your a, okay, if you apply. So, we cannot use this initial value theorem, and but you do not have, you have because you do not have x of 0 is 0. So, you can use this other condition to get this x pi. So, use this x pi which is taken as 1, right. So, you have that is 0, you have considered this to be 0, this is equal to pi times plus a times cos pi, that is minus 1. So, you have minus, that makes it a equal to pi. So, this implies x of t is equal to t minus t plus pi cos t is your solution, satisfying these boundary conditions. So, these are your boundary conditions, not initial conditions alone. So, you have a boundary conditions. Boundary conditions you can give, because it is a second order equation, you can give up to the first order. So, you can boundary conditions can be combination of x and dx by dt at t equal to 0, C1 plus C2 can be 0 at t equal to 0, x of t at t equal to 0. So, this is the boundary condition, it can be here with C1 C2 known. Not both of them are 0, if you have both of them 0, there is no boundary condition. So, one of them has to be non-zero. So, here in this case you have C1 is 0, C2 is equal to 1, and of course, this is given as a non-homogeneous boundary condition which we used here. Okay. So, other places we have similarly x pi equal to 0. So, you have a boundary condition at t equal to pi, that is here, and C2 is 0 and C1. So, this is equal to 0, this is the boundary condition, C1 equal to 1 and C2 is 0 in this case at t equal to pi. So, that is how you have provided these boundary conditions, and you get the solution just by applying this non-homogeneous second order linear equation with boundary conditions. You can derive Laplace transform by Laplace transform technique, you could derive its solution directly. Okay. So, this is how we can solve these differential equations, ordinary differential equations especially. You will get assignments to solve similar problems. Let us move on to find the solutions of partial differential equations. So, we can also use this Laplace transform to solve initial boundary conditions for partial differential equations of first order. So, to start with, we will use we will solve some first order partial differential equation. One can solve these partial differential equations, of course, some specific partial PDEs you can solve. First order means you have only first of all, what is a partial differential equation? You have a dependent variable of two variables, two independent variables, one or more. Okay. So, you have more than one independent variable. You should have more than one independent variable, xt are independent variables and only one dependent variable. Once you have this, you have this, and you can differentiate with respect to x, with respect to t. So, if you have a combination of this, if you have a relation between them, it is called a partial differential equation of order 1, because you have only first order derivatives. If you want to call this partial differential equation of second order, general equation is it involves also uxx, utt and uxt up to 2 derivatives. Okay. So, if you have all this, then you say that this equation is a partial differential equation of second order. So, as of now, so we will use the first order. So, this is the general form of this PDE. First order equation, how do we solve? So, what is the domain? So, if you want to use the Laplace transform, one of your domains should be 0 to infinity. So, let us do some examples, how do we solve this linear equation, simple partial differential equations of first order. So, we will solve some initial value problem, initial boundary value problem. Okay. We will solve, let me use this u is a dependent variable, ut plus x times ux equal to x, a domain is x positive and t is also positive. Now, what is given? So, you should have initial. So, if you look at this as your domain, this is your domain. So, x and t. So, t is your time variable. If you think initial, that is the initial condition at t equal to 0, because it is only one derivative, you should provide u at xt t equal to 0, you should provide some boundary condition. Let me use this 0. and boundary condition means at x equal to, x is the spatial domain, that is x equal to 0 means that is this line, along this line. So, you have a quarter plane t positive x positive, and you have on this line, you have on this line t equal to 0, you have 0, u is 0. On this line you have the boundary condition u at 0, x equal to 0 for all times t, that is also let us give it 0, t positive. So, here also you have 0, u 0 here and here. So, you want to find what is your x of t here. Okay. So, what is this that is that solving this solution of u that satisfies this differential equation, satisfying this initial condition and this boundary condition. So, that is why it is called initial boundary condition, initial boundary value problem. Problem for first order PDE. Okay. So, how do we solve this? We'll solution. We'll apply let us say t positive. You can also use for x also. For x also you can use because x is also from 0 to infinity, you can use Laplace transform. But if I try to avoid x, because if you use x, you have to take the Laplace transform on the right hand side. If I take a Laplace transform with respect to t variable, there is no t variable on the right hand side, that is 1. Laplace transform of 1 is simple 1 by x, otherwise here 1 by s square you will get. Okay. So, both ways you can do, you can try that way. So, let us apply a Laplace transform to the equation. To see that. So, if you do this, this is a partial derivative with respect to t. With respect to t, I am doing with respect to the variable t. Okay. What we get is this one. So, dou u by dou t, that is it's like du by dt. What is the Laplace transform of that? That is simply s times u bar of, in the place of x as it is, t variable is becoming s variable. So, I write like this, minus u at x t equal to 0, okay, and that is 0 by this initial condition, and then plus, if you take the Laplace transform of x into ux, that is simply x is a constant, and dou u by dou x, you are doing Laplace transform with respect to t variable. So, it is nothing to do with this dou x that comes out, and you only for the Laplace transform of u, that is u bar of x with respect to t you are doing. So, that is your s, and this is equal to x times Laplace transform of 1 with respect to s, that is 1 by s. So, this is what we have so far. I have used this initial condition. So, if you rewrite this as x times dou u bar by dou x plus s times u bar equal to x by s, because this is 0 by initial condition, by this condition this is actually 0. Okay. So, you end up this. So, if you divide s by x, so this is simply 1 by s. So, you can use, this is a ordinary differential equation, linear equation with respect to x. If you look at it, s as though s is simply some constant. So, you have doing with respect to x, right. So, x positive, this is your domain of this ODE, ordinary differential equation here. So, e power integrating factor is e power integral s by x dx. So, you get e power s ln x, that becomes x power s e power ln of x power s. So, you have x power s as your integrating factor. So, if you multiply to the equation x power s u bar of x s, for which if you take the derivative with respect to x, I multiply both sides of that equation. So, left hand side becomes this, right hand side x power s by s. So, you end up getting u bar of x s equal to, and of course, you have so if you integrate both sides, you get this one x power s, and then you have integral x power s by s dx plus arbitrary constant c. C is integration constant, arbitrary integration constant. Of course, this is C is because you are dealing with the partial differential equation, there is another variable, so this can be a function of s, okay. Arbitrary integration, integrating arbitrary function, okay. So, it can be a function. So, this implies u bar of x is equal to, this will be x power minus s by s times integral s x power s, derivative is, derivative of this is what is this derivative, integral x power s dx is simply it is like x power n. So, you have x power s plus 1 divided by s plus 1 and then plus c of s times this you bring it this side, that is become x power minus s. So, you have this becomes x divided by s into s plus 1 plus c of s times x power minus s is your u bar of x s. Now, you can use your other boundary condition. So, you have used the initial condition, now you can use the boundary condition u at 0 t, u at 0 t is your boundary condition. So, let me use this boundary condition since u at 0 t is 0 is your boundary condition. This implies you can apply your Laplace transform to this t variable for t is positive. So, you can apply even here. So, this becomes 0 s is also 0 because the Laplace transform of 0 is 0. So, now I use this here to see that left hand side is 0, which is equal to u bar of 0 s. I am putting x equal to 0 here. So, this is 0 because I put x equal to 0, you get c of s times x power, that is 0 power minus s, okay. So, 0 power minus s you do not know exactly what it is, right. So, you can put this you can apply this as x power s plus 1. So, you can remove this and you have x power s. Here you apply x equal to 0, so that you have Cs is simply 0. So, Cs is 0, that makes it 0. So, you have what you have end up is u bar of x s is x divided by s into s plus 1. So, this is nothing but x by s minus x by s plus 1. So, you can now invert, inversion will give, inversion gives, inverse of the Laplace transform gives u at x t, which is equal to x t minus x e power minus t. 1 by s is actually 1. So, you have x minus x times e power minus t. So, this is nothing but x times 1 minus e power minus t. So, this is your solution, this is the required solution for x positive and t positive as your solution of your partial differential equation with that initial and boundary data. So, this is how you solve this partial differential equation. Let me use one more example. How do you solve some other problems? So, let me use the same simple problems. Let me use. So, for example, let me start solve. I change a little bit this equation. So, I use x here, x u t plus u x equal to x is positive, t is positive, and let me use the same initial data, that is u at x 0 is 0 initial data, and the boundary data is also same. So, that let me use 0 t is also 0 for every x positive and here for every t positive. So, this if you want to solve, solution is just use Laplace transform gives, makes the equation becomes makes the equation into makes into what? You have to differentiate, you have to use the Laplace transform with respect to t, with respect to t makes the equation into. So, you have x is a constant here because, and then ut is s times u bar of x s minus u at x 0, that is 0. So, this I already used, So, I have this plus dou x of d dx of, so dou u bar of x s by dou x equal to, so again x by s, because Laplace transform of 1 is s. So, you get dou u bar by dou x plus x s u bar equal to x by s. This is your equation. So, you can use the same technique. So, integrating factor, you can solve this by integrating factor. So, x is positive, domain is 0 to infinity, integrating factor is e power integral x s ds, x s dx. So, s is a constant, so e power s times x square by 2. Okay. So, this is your integrating factor. You multiply both sides of your equation, left hand side becomes d dx of dou x of u bar times of x s times e power s x square by 2 is equal to e power s x square by 2 into x by s. So, you integrate both sides, you get you can see that u of x s times e power s x square by 2, which is equal to integral of x comes out e power s x square by 2 by s dx plus some constant, arbitrary constant, so it is not an arbitrary constant, it is an arbitrary function. Cs is arbitrary function, which you can get it from the boundary data. This what you get as this is equal to, you can easily see that 2x, this is simply integration is straightforward, s x square by 2 s square, right. So, you get s square. If you differentiate this, you get with respect to x s by 2 times 2x. So, 2 goes, you have sx, ss goes 1s, so you have x by s. So, this is exactly what you have. So, if you differentiate this, you will get this x times this integrand. So, this is your integration of this, and then plus you have c of s. So, this gives me u bar of x s as 1 by s square plus c of s divide times e power minus s x square by 2. So, we will use the other boundary condition, that is boundary condition is b u at 0 t is 0. So, that means u bar of 0 s is 0. So, if you use this condition here, so you see that left hand side is 0 and you get 1 by s square plus c of s, put x equal to 0, that is 1. So, this makes it c of s as minus 1 by s square. So, this implies you have what you get is u bar of x s is 1 by s square times, that is 1, c s is also 1 by s square, that is minus e power minus s x square by 2. So, this is your Laplace transform of u. So, if you invert this, you can get your solution. So, u at x t is t here, and you have a minus L inverse of e power minus s x square by 2 by s square. So, that is what is the solution, which is a function of t, of course, we should find. What is this Laplace inversion? We need to know what is this Laplace inversion. So, Laplace inversion of this, we use the Laplace transform of one of the property that we have used earlier, a Laplace transform of if Laplace transform of f of t is f bar of s, then a Laplace transform of f of t minus a times Heaviside function of t minus a, which is equal to e power minus a s times Laplace transform of f of t. Okay. So, this is exactly we use here. So, let me use so if you bring it here, we know that 1 by s square is the Laplace transform of t. Okay. So, this is Laplace transform of t, which is 1 by s square, and this is e power a, I use x square by 2 into s. So, this is equal to Laplace transform of here in the place of f of so this is the Laplace 1 by s square, I write it as Laplace transform of t. So, I can write here t minus f of so f is t, f of t is t Okay. So, f of t minus a is t minus a is x square by 2, and this is Heaviside function of t minus x square by 2. This is what you have. You take the inversion here. So, this makes it 0, both sides you have to take the inversion. So, this is Laplace transform of t is 1 by s square again. So, this is exactly what we have here. Okay. So, if I use this, you can see that u of x t becomes t minus x square by 2 times h of t minus x square by 2 for t positive, x positive. Okay. So, if you actually simplify it, so this becomes this is nothing but if t is less than x square by 2, that is 2t is less than x square, this is 0. So, you have only t here, and if 2t is bigger than x square or equal to x square, if it is 1, then you have t minus t plus x square by 2 that goes. So, you simply have x square by 2. So, this is your required solution for t positive and x positive. So, that is the solution of your partial differential equation, first order partial differential equation, which is here, this one, and then and with this initial data and boundary data. If you change your initial and boundary data and if you change the equation, you may see the complicacy of its inverse transform may be a little bit complicated. If it is complicated, you can use the general inversion. There you may have to use the contour integration technique to evaluate the contour integration, that integral using Bromwich contour, and then get your inversion, finally get a explicit solution for your partial differential equation of first order with of course boundary and initial data. So, this is how you can solve the first order partial differential equations. Second order linear equations also can be solved by this Laplace transform technique. So, any second order linear second order linear partial differential equation, you can put it into one of the typical equations such as a wave equation type or heat equation type or Laplace equation type. If you already know, if you have done a differential equations course, you might have seen how to reduce any second order partial differential equation, put it into one of the canonical forms. One form is it belongs to one class, that is one typical equation, that is hyperbolic type equation, that is wave equation. Another type is heat equation which is parabolic type equation, which is heat equation. Other one is elliptic type, the elliptic type of equations, that is a typical equation looks like a Laplace equation. Okay. Second order term looks like a Laplace equation. So, we will see one of so at least two these typical equations with some initial and boundary data we will be solving in the next video. For certain problems we will solve, and then we will move on to we will move on to apply this Laplace transform to solve some integral equations. Okay. Thank you so much.